Hello again. Welcome to your favorite YouTube channel, I'm sure at least for fall of 2020. Another video here that we're going to chat about with regard to local winds. Purposefully made one video last evening, watched a little bit of the Chicago Bears, and now here I am giving you a, look at Delta as it approaches the Louisiana coastline. Again, you can see the ragged coastline of Louisiana here, Texas, and then Mexico down here. So again, as somewhat promised, Delta has become a pretty large storm. One thing you can see is a lot of this deeper convection. This is again an infrared, so we're looking at cloud top temperatures, and so we got really cold, tall cloud tops, but it's been tough to really get this convection to fully wrap around. But that being said, without going into great detail, as of right now, 7:22 in the morning on Friday, we're looking at a 120 mile an hour sustained Category 3 hurricane. Still expected to weaken a little bit due to some cooler waters and some greater shear. This wind blowing with height changes as we get closer and closer to shore. So still going to be a rough evening for a lot of folks down in Louisiana. So something to keep in your thoughts. But as we move back towards our lecture here, looking at mountain and valley breezes, we ended up talking about land sea breezes and frictional effects, but we're going to get a little bit more into terrain, because terrain is a definite catalyst for a lot of these notable local winds, and also then get into some smaller scale stuff down to the micro scale. And we'll be pretty brief with some of that. But mountain and valley breezes are definitely an important local wind phenomenon as well, because these can, pretty much dictate the weather that occurs in areas that have complex terrain. And so what happens with mountain and valley breezes is we refer to the breeze just like we did with the land sea breezes, where it is originating from. So a valley breeze originates from the valleys, moving up the mountain, and a mountain breeze originates from the top of the mountain and moves down the mountain. The valley breeze occurs during the day. Here we have warm air, and that warming of the air is going to cause rising motion, again, all related to air density, and that's going to potentially start to create a lot of times over the terrain where we get some thunderstorms in the afternoon. For instance, the Black Hills of South Dakota, beautiful place if you ever have the chance to visit, far southwestern South Dakota, quite common to just simply see thunderstorms develop over the terrain, but areas that are not far away from the terrain get significantly less precipitation, and even these can be pretty isolated. However, as the sun goes down, temperatures cool off, we start to see some greater cooling up on the top portions of the mountain, and that's going to create this mountain breeze, this drainage type wind that can funnel down into the valleys, and this is why we oftentimes see some pretty complex winds in areas of terrain. Katabatic winds are a special type of mountain wind. Here, again, when you have some larger areas of cooler temperatures due to the fact that we traditionally see temperatures cool off as you get higher and higher in altitude. And so when we get these elevation differences, we can get simply snow-covered cloud or mountaintops, generally cooler temperatures. And so if you get these areas with more of a plateau type feature, a large, flatter area that can have much cooler temperatures, that cool air is going to effectively serve to be higher pressure, the greater density of the air. And so what happens here with a katabatic wind is that air that's more dense, you get your pressure gradient to set up, and that's going to effectively force air off this cold, higher terrain down towards down towards lower terrain. And what that can do is actually institute this warmer air. What happens is this is referred to as compressional warming. As the air comes down the slope, it compresses, and when we compress a gas, it's going to serve to warm it. We're going to push those molecules closer and closer together. And so, in this image, it's not to where you end up with any balmy conditions at the lower terrain, but the katabatic winds can be quite strong and produce some significant local warming in the lee of the terrain. One of the types of mountain winds that's more common here in areas of the United States, in fact, areas not too far from, say, the Black Hills that I mentioned a couple slides ago, are the Chinook, or the Foehn winds. Kind of a fun word to say there. We could get an umlaut on that as well. And so this is going to be one of the reasons we see every so often some intense warming conditions across the plains of the United States. An orographic barrier, orography, fancy word for mountains or higher elevations, and so we have a really notable orographic barrier in the Rocky Mountains. And so this graphic in the bottom left is a general idea of what's happening. We sometimes are going to have this upward motion as rain comes on the windward side. It's going to create clouds, precipitation. We're going to talk a lot about this here soon in stability. And so we have the temperatures cool as air goes up the mountain, but then as it sinks down the mountain, it starts to warm, and it's not going to be saturated, and so we can warm at a rapid rate. And so you often will end up with warmer conditions on the leeward side, along with dry conditions, than you do on the windward side. And so we see these Chinook winds, well, on the eastern slope of the Rockies. That's where we actually come up with the term Chinook. Again, areas such as the western South Dakota, Nebraska, Kansas can be areas that really warm up nicely, even areas in Colorado and portions of Wyoming, and these can extend much, much further east in many ways as well. These are referred to as different names. A lot of what you'll see with these local winds have, well, local names. And so in Europe, they're referred to as the Föhn. Argentina, we refer to as the Zonda. If you understand the Chinook wind, again, we're going to focus here on the weather here in the United States, but understand that it's a similar wind in just different areas. These are quite famous in some areas to the west here of Valpo. The fact that you can have temperatures rise 30, 40, 50 degrees in a relatively short amount of time, and so they can be referred to as snow eaters. You have a day or a series of days where you get a good snowstorm across the plains. It drops rapidly at well below zero, and then you get these strong winds coming down that rapidly warm and erode the snowfall, snowpack. And part of that is related to the fact that, again, this is such a dry wind. And so the schematic in the bottom right, I'm going to purposefully kind of gloss over in many ways. What you end up seeing is that you see these arrows here, these couple arrows going upward, showing we have warm but not really warm, but some moisture in the air as it's ascending. But then as it comes down the mountain, not only is it much warmer, again, it is much drier. And so that dry air does even better to erode some of that snow. And so the Chinook winds are not an uncommon thing at all. These are actually quite regularly occurring depending on the airflow across the terrain. We saw some of this actually earlier this year when we had some of that crazy weather back in September around Denver and Boulder, where they were having some heavy snowfall, warmed up rapidly again due to this compressional type warming. The Santa Ana winds have regularly been in the news over the last few years. The Santa Ana winds are going to form when you have a staunch high pressure that basically settles in over the Great Basin, and that produces a pressure gradient blowing from northeast to southwest. And so here we see a warm, dry air, again, from the east or northeast down the mountains. And so just like some of our earlier local winds, when we get this air to come down the mountains, it can compress, warm up, it'll be very dry in nature, and these can be quite scary for some folks in Southern California. And unfortunately, we've dealt with Santa Ana winds helping to either generate or complicate some of the fire conditions out there. Again, the fact that these are originating from areas over the Great Basin, again, say Utah, Nevada, northern Arizona, means you're coming from areas that are not considered to be moist in any way, shape, or form. They're already dry air that just continues to dry out even more. And so here you can see dries out the vegetation. You can see the fires. You can see the blow off of the smoke in the schematic in the lower right. The little red dots indicating where the source of the fires would be. And so this is going to make for hot conditions across the area. They can rapidly change. There are instances with the Santa Ana winds, you can see the winds approaching 100 miles an hour as they come down through some of the mountains and valleys. Dangerous wind, especially in times such as these when we have already a great setup for, unfortunately, bad fire conditions across much of the state. These, though, are, however, going to be pretty much confined towards areas down around Los Angeles and San Diego. We're not going to see Santa Ana winds up around San Francisco and Oakland. Again, looking at that smoke, this is actually from 2007. Massive fires that were the red dots, especially down there you can see between Ramona and Rancho Bernardo. Again, significant issues due to these Santa Ana winds, which will cause these fires to spread rapidly. A couple other things with regard to some local winds that occur primarily in desert regions. Again, more arid conditions, warm to hot conditions, and so you see dust storms, sandstorms, dust devils, and haboobs. Haboob there would be what you're seeing in the lower left, these walls of dust that will basically look like they're coming out of some type of movie. menacing, and they can drop visibility to 0. This would be a real image there in the bottom left near Phoenix, Arizona. Haboobs are going to be quite common in the United States across the Southwest, extending all the way through New Mexico into, say, the Panhandle of Texas. They are also completely a common occurrence across areas such as the Middle East. Again, going to be occurring due to thunderstorms as they dissipate and cause outflow. And that outflow is going to help to cause the sand and dust to kick up and create these walls that can press out many, many miles from a decaying thunderstorm. Dust devils in the upper right are going to be formed due to simply really hot localized conditions that we can start to spin up some local tornado-like features, but the formation of a dust devil is not tornado-like. In fact, as I have here in the schematic, it is not a tornado. We'll talk about what constitutes a tornado later on. We have to have what's known as a mesocyclone associated with a tornado. Dust devil winds are going to be generally much lighter than what you would see with a tornado as well. You can definitely see dust devils if you go out into the plains of the United States across areas such as the summer. You'll see them simply on the sides of the roads. Again, many other parts of the world, Middle East, areas of Asia, dust devils are very, very common as well. And so we're going to take a few minutes here. We'll get through this relatively quickly, small scale winds. And so when we talk about the earlier winds, these are more on that mesoscale, and we're going to work our way here briefly into that microscale, going back to the last video. And so the things that occur when we start to deal with the smallest scale winds is that we're looking at very localized interactions with the surface. And we know already that when we have to bring the surface into the equation, that friction must be accounted for. And frictional effects can be quite variable. We don't really get into that type of detail with force balances because it's not important on those scales. But as we drill down to the local scale, it is going to be quite important whether or not it's smooth terrain versus rough terrain. Turbulent motion, chaotic motion that occurs in the lower portions of the atmosphere in particular. This is quite important to things such as aviation meteorology, but this is also going to be something that we deal with both in terms of mechanical, where we have different wind speeds, shear, things such as that, and also thermal. Simply daytime heating can produce some of these localized small-scale wind effects. And so what we can end up with is what we're going to see on a few of the subsequent slides here. Some wind erosion, sand ripples if we have large deserts with some of these local small-scale wind effects. Snow also, snow ripples, snow dunes, rollers, fences. If you like snow, we get to talk about snow for a couple of minutes here. Again, things that for the purposes of this class, get a general feel for what's going on, but it's not one of those things where you should spend a very large portion of your time studying some of these small-scale winds. Windbreaks and shelter belts as well. And so let's take a quick moment and just make clear what we're talking about when we refer to turbulence, and again, what is the boundary layer. And so I've alluded to it briefly in the past. When we refer to the boundary layer, we're simply talking about the layer in the troposphere that is going to be effectively impacted by frictional effects. And so here we see a very low budget figure, but still accurate. We have someone though who's about half the height of a thunderstorm. But we're going to have that boundary layer be a pretty shallow layer before you get to here what they refer to as the free atmosphere. When we refer to turbulence, again, we're simply talking about chaotic motions, unanticipated upward, downward bumps, swirls that you might see occurring in the corner of a building. And so we're really focusing on these in the planetary boundary layer again, due to the fact that frictional effects are quite important. And so what we see here is an example of winds on the x-axis and then height on the y-axis. And in this example, you can see when we have minimal mixing, friction is going to really slow things down as you're near the surface with some stronger winds aloft. And as we mix things up, this is kind of what we remember back with diurnal heating. We can make the winds a little stronger down at the surface, but a little bit weaker maybe aloft as we mix that momentum downward. But what you can see in both of these is that regardless of the mixing, we have lighter winds down by the surface. And that friction is slowing things down, even increasing them as you get up a half kilometer or a kilometer above the surface. Frictional effects are going to lessen. And so vertical mixing is simply going to increase the amount of vertical mixing. It's going to help to churn things up, bring a little bit of that greater momentum air that's not as impacted by friction down to the surface. And so sometimes when you're in an area of rough terrain, you're going to be able to mix down some stronger winds. This is a little bit true, kind of as you saw over the plains. You remember the opening slide from video 1, being able to bring some of that air that's originating over the Rocky Mountains and start to make some of the stronger winds as they come out over the plains, mixing some of those winds downward, even on scales that large. So a few other local small-scale winds. Here we have a wind dune that is occurring. The idea that what's happening here is that when these ripples start to occur in the sand, it's going to locally slow down the motions along the surface. And so here you can see that the wind would be blowing here from left to right. You can see the ripples in the sand and these dune features that form as the wind gets the sand gets slowed down and starts to descend in the lee of the dune. And it's kind of neat to see the ripples actually being able to help signify what the flow would be in here. And so if you've never been up to the Indiana Dunes, now National Park, definitely worth the time, even though you're not going to see any landscape that looks like what you have here in the image. Still some fascinating dunes that have formed over the years due to flow related to both friction, but as well as Lake Michigan. Snow rollers. Here we basically have these large cylindrical rolls. These are, well, you might think someone trying to make a random snowman and not completing the task here, but what you effectively have is some type of probably at least mild hill setup, and what you have is that the wind is going to start things up. If the snow is of the right consistency, meaning it has enough moisture to be able to pack, you can start to create what's known as snow rollers as they literally roll down the terrain. Looking at complex flow around small objects. This is going to be the idea that in the morning, again, usually calmer conditions. Again, I'm looking outside of my house right now, and the flags at the moment are basically standing still. And that will change significantly as we get later in the day today due to any number of reasons. An increasing pressure gradient is part of it, but very much what's going on in this image is part of the equation as well. In the morning, quiet winds, weak flow is going to create these eddies. This is a term we use a lot in meteorology, turbulent eddies. And so this is going to force the flow upward, compress your air as it goes over this building, and as it comes down around the building, we may get some little swirlies. Not a necessarily technical term, but that's what we kind of think of them as. Afternoon, things warm up. We're going to start to, again, bring down some of that air that's higher aloft that has greater wind speeds. Winds are going to increase in the afternoon as there's more unstable conditions. We're going to talk again starting next week about stability, and that's going to create a stronger flow and create these greater swirly features, especially in the lee of buildings. And so again, if you've ever been over to your favorite store and it's breezy outside and you're ready to walk in and you get your mask on and you see in the corner this swirling newspapers and garbage bags, we just get a lot of this turbulent, chaotic, eddy type behavior that happens when you have complex terrain. And complex terrain can mean buildings, it can mean cars, it can mean any number of features that are outside that we have to deal with. Another thing going back towards snow fences. Here we have the idea of we're trying to simply slow down the wind. This may create some chaotic motions in the lee side of the snow fence, but what we're ultimately trying to do here is put this snow fence in the direction in which wind is trying to blow air on, or blow snow, I should say, and air, on maybe a major interstate. And so here you would see an example where the snow is coming from areas here off on the right side of the image. As the snow and the air impact, this blowing snow impact this snow fence, it helps to slow things down. And so that will start to cause the fallout of the snow and create these pretty significant mounds, these drifts. And so there's actually a lot of math and science that go on to the distance these snow fences should be placed alongside a road. I alluded to in the last video, if you've ever driven down I-65 towards the Fowler Wind Farm, here if you ever drive down I-65, you will see a notable amount of snow fences, and most of them are going to be located on the west side of the interstate. And the idea being that we're in an area that we're preferring westerly or northwesterly winds, particularly in the winter months, and therefore we're trying to keep that snow when it gets open, or when there's open terrain and it can blow strong in winter. We're trying to keep that snow off of the interstate. So a lot of the farmers and the landowners down there are going to put up these snow fences, more than likely in conjunction with some government officials, to try and keep I-65 a little more safe, because it can be pretty precarious driving in wintertime. Again, in and around terrain, we can see here, this is kind of related a little bit more to mountain waves. Mountain waves can create some notable turbulence. The idea that the air is a fluid and we compress that fluid as it comes over the terrain, and we can create a crest, but then it's going to try to basically return to its original state due to the fact that it's being forced against its will over the terrain, and then it's going to sink, and we can start to create this wave, almost like a ducting phenomenon. And so we can create these, what are referred to as eddies or rotors. These can be very dangerous, for instance, to aircraft. If there's notable mountain wave turbulence, aircraft will simply try to fly above it or will avoid the area completely, because this can completely be something that takes an aircraft out of control of any skilled pilot. And so we'll talk again a little bit more about stability here soon, and this requires a stable layer. And so we're going to talk a lot about stable layers and unstable layers of the atmosphere before long. And so I conclude, since I'm getting a little long on this video as well, I told you they'd be a little longer today. We'll take a break again before too long. With some local winds. I will say up front that you do not need to memorize these for any exams. That would be a poor use of your study time. But read through them. Some of these are kind of interesting. For instance, highlights say the Tehuantepec, one of the more fun named winds that we have here. This is going to be down Mexican Guatemalan mountains and out towards the Gulf of Tehuantepec. If any of you have Professor Balzell-Scholes for lab, she actually did some of her research when she was in graduate school on Tehuantepecers. A pretty fascinating setup here. So that is all I have for today. Hopefully you've enjoyed some of these videos on local winds, and we will see you on Monday. Take care.